is 9:30. Let's start. Welcome to Block 2 and the Algorithms and Data Structures course. I want to start off with a bit of high-level information. So what is this course about? In a typical computer science degree, you will see courses called Algorithms and Data Structures. This course is quite different from those. So we will be doing a little bit of that stuff, but we have a lot less time, and we also have a different emphasis. One thing that is going to be different is the course will be more applied. We're not going to be proving things. Another difference is that this course is going to be Python specific. Typically, these types of courses give general principles that can apply to all kinds of things. That would be great, but you all really need to know Python, so we're actually going to spend some time on Python. A lot of students struggled with this course in the past for some of the reasons I listed there. The difficulty, the pace, didn't seem relevant to data science, and just struggled with the Python coding in general. So I just wanted to tell you some of the changes that have been made to the course this year. The lectures have been completely rewritten, but I posted last year's lectures in the repo as well if you want to look at them. They are PDF slides. And the lectures have essentially, I've tried to make them more applied and more tied to the labs. Also, there's sort of a new goal of the course, which is this Python-specific stuff, or in general, how do I deal with slow code? So I do something, it's too slow, what's my next step? One of the goals of the course is to try to help you decide what your next step should be in that situation. This course also had a bunch of lab questions that said, implement such and such algorithm from scratch. And those are probably the ones that people struggled with the most last time. And they're not essential to what I want you to get out of this course necessarily. So I've made those optional and added other stuff to the labs instead. That's this more Python-specific content in the course. So if you like that, it's still there. If you don't, it's optional. Just ignore it. And finally, as you know, the programming course that comes before this had been made a lot more intense this year. So I'm hoping that will also help prepare everyone for this course. Any questions before we get started?
So how is it related to data science?
So how's it related to data science? You're going to see some of the data structures we talk about, like graphs. You could very well encounter data in that form, like social networks, and we're going to have stuff like that in the lab. But in general, how is it related to data science? Well, one is that you are going to be programming stuff, and you are going to run into code that is too slow, and you are going to have to decide what to do. Or you are going to be programming things and looking at other people's code, and it's going to do things in a way that up to now you might not understand what this person was doing, and we're going to talk about some new programming ideas in this course that could help you understand other people's code. And then the last thing is, in 5.11, we talked about a bunch of data types like set, dictionary, list, numpy array. But we didn't talk that much about how to choose which one you should use when you're trying to accomplish something. And that's another thing that you need to know when programming for data science, and something we're going to talk about for this course. So what can each data structure do for you, essentially? What was your name again?
My name?
Yeah.
Jackie.
Jackie. Okay, let's launch into it. So here's a common thing that you might want to do. You have a bunch of stuff, in this case just integers, but it could be anything, and you want to know, is a certain item in there or not? So what I'm doing here is I'm making n. Oh, this is a better. By the way, you can put these underscores in Python just for readability. They don't change the code. So n is 10 million, and I'm basically making a list with the numbers from 0 to 10 million minus 1. And then this in syntax in Python just tells me, is -1 in x or not? In this case, it's false because I started the numbers from 0. So that's all good. But how long did this take? So time it, or percent time it. It's an IPython thing. I don't think we talked about it yet, but it is not part of Python, but it is part of IPython, and Jupyter is running IPython. So long story short, if you're using Jupyter, you can use time it. And it just times how long something takes. That's it. So I'm going to run that. And what time it does is it runs the thing a bunch of times to get a good measurement of how long it takes. Gets you kind of like a error estimate and stuff. Okay, it says it takes 120 milliseconds plus or minus 10 milliseconds to check whether or not -1 is in this list of 10 million things. So now I have a new code that is exactly the same as this up here, except that I'm making a set instead of a list. And I can do the same thing. There's -1 in x, and it's going to tell me the same thing because the in operator in Python works for a bunch of things, works for lists, sets, et cetera, et cetera. Just a minute, and I'm going to time this. And again, it's running it a bunch of times. 54, that's half. Oh, no, wait a minute. That m has changed into an n. So apparently this took 2 million times faster or something like that. It went from 100 milliseconds to 54 nanoseconds. So I had to use time it because even 100 milliseconds is kind of too fast for us to perceive, really. But OK, we just made something 2 million times faster by just changing one word from list to set. So why is that? Why is it so much faster? Or in this case, should I always use set? Because set just seems better. This is the types of questions we're going to be digging into in this course. Yeah, Anas.
What do you mean by 10 loops each in the first one and then the 10 million?
Oh, I see. So 10 loops each versus 10 million. So time it basically decides how much patience we humans have to wait, which is like a couple of seconds. And it just keeps doing the thing over and over again until it reaches a couple of seconds. So if something's really fast, it'll do it more times to average how long it takes. So it's just telling you I did it that many times and then averaged them. OK, so yes, I'm showing you this as sort of a roadmap for where we're going in this course. So how could I have predicted this outcome? Hopefully by the end of the course, you could have just looked at this code and said, oh, of course, that's going to be way faster with the set and the list. And not just qualitatively, but quantitatively, what if I double the size of n? So that was 10 million. What about 20 million? How much slower is that going to be? We kind of feel that if I have a bigger list of things to search through, it's going to take longer. But how much longer? We're going to try to quantify that in this course, and in fact, starting today. And then the third thing is like, why did this happen? So how do you make a set? And that's more the stuff that a typical algorithms course that would be the main focus. But in our course, that's going to be more tangential. And we'll kind of touch on that, but we won't go into it in full detail for all the data structures that we talk about. So by the way, the course is called Algorithms and Data Structures, and data structures are stuff that you put data in, essentially, like a list and set, and maybe the innards of the list or the set could also be called data structures. OK, so this note here is just saying that the demo was cheating a little bit because I only timed the in operation. I didn't actually time how long it takes to create the data structure. And actually, creating the set takes a little bit longer than creating the list. So there's that give and take there. And we'll talk about that a little bit more as well. So any questions before we move on to the next demo? OK. Demo number 2. Oh, before we do demo number 2, there's an aside that we need to talk about, which is min and argmin. So here's x. It is a list with, I don't know what, 7 things in it. And I can use min, which is Python's min, and it gives me the smallest element in the list, which in this case is 0.1. And there's also NumPy's min, which does pretty much the same thing. In general, when we're doing computations, we typically use the NumPy version of the function we're calling because they have a bunch of benefits that we'll talk about a little bit, but sum, min, max, all these kind of things. I'll typically just use the NumPy one unless I don't even want to install NumPy or something like that. Okay, so there's something else called argmin, which some of you may not have heard of. And what that means, it's the index of the minimum. So 0.1 is the smallest element. That's like the value of it. But which element was that? It was element number 3, because remember we start from 0. So 0, 0, 1, 2, 3. So argmin just says the index of the min, and we can take x of 3 and see that it is indeed 0.1. So this is something that's super useful, and you'll see it here and there in the program. Okay, back to the point. So here I have making n 20,000. I'm making a list of these numbers. Now I'm shuffling them. So by the way, numpy.random.shuffle is one of those functions that modifies the thing itself. Remember, we talked about that in the last course. Some functions can modify x itself. So when I look at x, it's no longer in order. It's just some numbers between 0 and 20,000 minus 1. And here's some code that I don't want to go into great detail right now. But it's just kind of slow. OK, it's running, it's running. We'll have to wait for it to finish. I'm assuming my past self made it not unreasonably slow, but we'll have to wait and see. There we go. OK, so what this mysterious code has done is it has actually sorted x back in order. And again, we'll go into this more later, but very briefly, it's looping through x. It's finding the smallest thing. And then well, it's finding the smallest thing past a certain point because the first part has already been sorted. So it's taking the rest, finding the smallest thing, and then it's just saying, put that in this location and swap it with whatever was there. Now, these are sorted. We have the stuff left. Find the smallest thing of what's left, put that there. Find the smallest thing, put that there. Find the smallest thing, put that there. So that's what I'm using argmin for, is to find the index of the smallest thing, because I want to know actually what position it was in so that I can swap two things. And this is another thing that's kind of cute in Python, is that you can swap two things without a temp variable. So if you started learning with C or whatever, there's this thing in programming about swapping. In Python, I can just use the syntax that's highlighted, and it's going to swap the two numbers. OK, if you don't follow this code perfectly, that's fine, because that's not really the point. The point was how long we waited for that code to run, which, if you recall, was, I don't know, 5, 6 seconds. 10 seconds, I don't know. So now I'm going to shuffle it up again, muck it all up again. I can actually show you that it's shuffled again. And now I'm going to call x.sort, which is a built-in NumPy function. And let's see how long this takes. Imperceptibly fast. So apparently, my code is a lot worse than the NumPy code. And we're going to dig more into that in this course. And it's actually worse for a couple of reasons. It is actually worse because, well, we'll talk about it. We'll get there. But OK, so again, how could I have predicted this? What's going to happen if I double n? And could I write a sort as good as the NumPy sort? These are, again, the type of questions that we want to tackle in this course. So last demo. All right, any questions on this demo, actually, before we go on? So hopefully, at least this is convincing you that doing it right actually matters, because you can see how much faster the code was. My code wasn't incorrect. It was just slow. OK, so demo number 3. N is 10 million. We make some random numbers. in x, we make y a bunch of zeros. So here's the first 10 elements of x. Here's the first 10 elements of y. And my goal here is going to be to just multiply x by 2. That's it. That's my goal. X is a big NumPy array with 10 million numbers in it. I just want to multiply each of those numbers by 2. So I could make a loop over n and just say the corresponding element in y is the corresponding element in x over 2. And here it goes. It's running, running, running. Done. OK, I took, I guess, 3 seconds or so. And then we can do what we talked about in 5.11, which is take advantage of the fact that NumPy just allows you to do x times 2, and it knows what you mean is multiply each element. And this is just instantaneous. And again, we'll want to understand why. And the interesting thing about this is that sometimes the faster one is faster because of a better data structure. That was case number 1, where the set was a more appropriate data structure than the list. Sometimes it was faster because it was a better algorithm. So the sorting algorithm that NumPy uses is actually a different algorithm than the sorting that I use. And sometimes it's better because of a better implementation, which is this last thing. So it's the same algorithm, you're just multiplying every number by 2, this one, then this one, then this one. I mean, there's no real algorithm involved. But someone implemented it in a much better way that just made it way faster. So we're going to talk about these 3 prongs throughout the whole course. Good data structures, good algorithms, and good implementations. And those will all come together in the last lab in a hopefully magnificent way, so you can see, so you can bring it all together. OK, any questions about this? Furkan.
Yes. So I just want to know that in this course, will we also focus on how the memory usage will have effect on the code?
Well, we focus on memory usage. We will talk about memory usage. In fact, we will talk about it today. But we will not really talk about how it works, like how memory is allocated on the computer. We'll just talk about this type of thing takes up more space than that type of thing and try to quantify it a little bit.
So just for the code optimization purpose?
Not just for code optimization. Also, I mean, you might just run out of memory sometimes, and then your code will not work. So that's another reason why you might care. OK. So the main thing we need to do today is talk about time complexity. Time complexity means essentially talking about how long do those codes take to run as a function of n. So we had n as 10 million, as I said, or whatever. But how is it actually growing with n? If I change it from 1 million to 10 million to 100 million, how does the speed change? That's the main thing we tend to talk about when we talk about how fast code is. So let's talk about this question. What happens if I double n? What happens to the number of steps? So there's no reason why you would know this yet, but I think it'll still be fun to have people just take some guesses, and then by the end we're going to sort it all out properly. So here's the first one, finding out whether a number was in the list. So I had a list of a certain length n, for example, 1 million things in my list or 20 million things in my list, and I just want to check is something in there? Is -1 in here or not? Is hello in here or not? If I double n, what do you think happens to how long this is going to take? Tom?
Does it exponentially grow?
Does it exponentially grow? It doesn't, but we will talk about exponential growth today.
Do it double?
Does it double? Yes. What's your name again?
Sri.
Sri. Yes, it doubles. So basically, you can think of searching in a list as, well, is it this? No. Is it this? No. Is it this? No. Is it this? No. Is it this? Maybe yes, or maybe in this case, we're just getting to the end because I was searching for something that wasn't even in there. So if I have this many things in my list, it's going to take a certain amount of time. If I double the length of the list, it's going to take double as long because I just have to look through twice as many things and say, is it this? Is it this? Is it this? Again, feel free to guess. I don't expect you to know the answers because we haven't talked about these things yet. So answer doubles. Okay, next one, finding whether numbers in a set. So exact same thing, except I had that set data structure instead of a list, and now I double the size of the set. How do you think the running time is going to change if I double the number of things in the set? What's your name?
Arun.
Arun.
Yeah, I think it should be pretty much same.
Should be pretty much the same. Yes, so that is actually true, and we will talk about that on Thursday. And that's kind of a mind-blowing fact because, I mean, the list thing kind of makes sense. If I have twice as many things to look through, it should take twice as long. What is this amazing set that I have twice as many things in there, and it takes pretty much the same amount of time to look through? Well, we will talk about it. And by the way, that's why it was so fast, because it didn't really matter that much that there was 20 million things in there. Okay, so the sorting. So we had n numbers just shuffled in a NumPy array or a list or whatever, and we just wanted to sort them so that they were in order. If I have 1,000 numbers and I sort them, or now I have 2,000 numbers and I sort them, first of all using my code, so that code I showed you that used the argmin, how much longer do you think it would take if I doubled n? James?
4 times.
4 times, yes. That is correct, and well, we'll talk about why later, but that is correct. Of course, yeah, some of you have seen this stuff before and some of you haven't. Okay, how about NumPy sort? So that seemed way faster than mine. Using my code, doubling n, it went 4 times faster. What about using the NumPy built-in sort? What do you think happens to the time if I double n?
Is it recursive?
Log time, okay. Anyone else?
Is
Danny?
it recursive?
Is it recursive? Maybe, but I want to know what happens if I double
Right.
n.
Well, that affects.
2 times.
Is it the
No takers? Okay, so what happens in that case is it slightly more than doubles. You can pretty much say it doubles and it wouldn't be that wrong. And we'll talk about that more. But that's great because this thing, when I double, with my code, when I double the size, it goes up 4 times. So if I double it and double it and double it, it's going up 4 times, 4 times, 4 times. But with Python's code, if I double the size, it just slightly more than doubles, which is much better because as I grow n, the time isn't growing as fast. And so by the time I got to 20,000 things that I was sorting, it was way faster than my code. And we'll talk about that hopefully on Thursday as well. Okay, so now doubling an array with a loop. So I had my x, it had 10 million random numbers in it. I was looping through them and just multiplying each one by 2. So if I had an array that was twice as big, how much slower or what would happen to the running time?
I think it would double.
Yes, but Sam, right? Yeah. Yes, it would double. That's right. So this is very similar to the searching in a list. I'm just cranking through one at a time, multiplying this number by 2, multiplying this number by 2, multiplying this number by 2. And if I have twice as much stuff that I have to deal with, it's going to take twice as long. So that's right. That would also double. And how about the last one? So this NumPy times 2 thing that was super fast, what do you think happens there if I double the size of the array?
Remains the same.
Remains the same. Anyone else? So it also doubles. Because again, I still have to multiply every number by 2. The amount of stuff I have to do, I had this many numbers, and I have to do that amount of work to each one. I have to multiply it by 2, and I have twice as many numbers I have to deal with. So I was trying to trip you up. I think maybe why you said that is because, well, it was so much faster, so it should have a different answer.
Like NumPy will do it in parallel, like in parallelized operation.
Well, you're getting ahead of ourselves, but it can't really avoid this doubling at the end of the day, I think. My point of showing this last part is to say, in the first parts with the searching and the sorting. The faster one actually grew at a slower rate. But in this case, I just have to multiply all these numbers, right? And I have that many numbers to deal with. So in terms of the growth, it's not really different. It's purely a matter of implementation. So talking about the growth is very useful and almost always is going to tell you a lot about how fast your code will be. But sometimes there's just some amount of work you have to do. And strangely, there's different ways you can multiply a bunch of things by 2, and one of them is bajillion times faster than the other one, which is pretty surprising. And we're going to talk about that on the last day of this course. Any questions about this? So again, there's no reason why you should have known the answers to these, but I'm just presenting them as a sort of roadmap for the course, that by the end of the course, I think you would be able to answer these. Questions, comments? Okay. Let's keep going. We'll take the break a bit later. We're doing well on time. Okay, so the next thing we want to talk about is something called big O notation. Again, maybe some of you have seen this in algorithms course. I guess probably most of you have it. First of all, for those who care, and I do not include myself in that group necessarily, there's a bunch of things other than big O that you may run into, like small o, small omega, big omega, blah, blah, blah. We're just going to do everything with big O and not worry about the distinctions between all of those things, but you can read up on them if you want to. So we're just going to try to keep it simple. We have very limited time in this course, and so whenever we talk about time complexity, we'll just use big O. And so what big O does is it tells us, technically, again, it's actually an upper bound, but we're just going to ignore that and say it tells you an approximate number of steps that the algorithm performs as a function of input size. So it's kind of a function of n that tells you roughly how slow is this thing going to be as a function of n. Because the number of steps that the algorithm has to take is kind of a proxy for how many seconds or minutes it's going to take, because the more things you have to do, the longer time you're going to have to sit there waiting. Okay, so we just did this whole doubling exercise. So how do we turn that into big O? So, well, even before what's on the board here, we talked about searching in the list. That was the first thing. We said if I double the size of the list, that's going to take twice as long. So that's called O of n. And it's called O of n because if you just draw n, I'm basically just drawing the line y equals x. I'm drawing f of n equals n itself. So if this is the number of steps, and this is the size of the input, or the size of the list, or the size of the array, or whatever, if it's just a straight line like y equals x, then yes, if I double, this is 10, and this is 20, then this is also going to be 10, and this is also going to be 20. So that thing we just talked about with the list a few minutes ago, that if I double the size of the list, it's going to take twice as long, that's basically saying how long it takes is roughly proportional to n, because that's what this function means. If I double n, then I double how long I'm taking. What we have on the slide here was that 4x thing. That was my sorting algorithm that was painfully slow that we waited for. My sorting algorithm we would call O of n squared. And why would we call it O of n squared? Because we said, we didn't say y yet, but we said that if I double n, then I actually have to wait 4 times as long. And if you just think about what n squared looks like, it's a parabola. I'm not going to draw the other half of the parabola because we're not going to have an array of negative size on our hands. But what does the function n squared mean? It means, well, I have the point 1, 1, and then I have the point 2, 4, and so on. So what a parabola does is it says if I double the input size, then the value of the parabola is going to be 4 times as much. So if you say the running time of this code is big O of n squared, that's pretty much the same thing as saying if I double n, then the running time is going to be 4 times what it used to be, like my sorting code. And if you say the running time of my code is big O of n, that's pretty much the same thing as saying if I double n, then my running time is going to be doubled. And that's what we had with the searching through the list and the multiplying all the elements of something by 2. Questions about this? Rock.
Yeah. Why it has to be n squared, not 4n?
Aha! Why does it have to be n squared, not 4n? Okay, so just forgetting about running times for a minute, but just thinking about functions, right? If I have a function f of x equals x, and I have the function f of x equals 4x, both of the, so let me draw them for you. Here's x, and here's 4x. So they're both lines. They both have the property that, so if x is 1, 4x is 4. If x is 2, 4x is 8. So it still has that property that when I double x, the running time doubles. It's essentially the same shape curve as x. It's just 4 times larger. But the truth is, we don't care what the number is in front, if it's 4x or 1,000,000x or 0.01x, because we don't actually have proper units on this big O anyway. It's not like we're telling me how many seconds the code is going to take. It's not like it says it's going to take 2.7n, and that's going to be the number of seconds. We don't really we're not really getting to that level of detail anyway. We're just talking about growth. And so as far as growth is concerned, these two things are the same. They're only scaled versions of each other. But this is actually a different shape of a function. This function has a different property that when you double the input, the output goes up 4 times. The function 4x has the property that when you double the input, it just doubles the output. Did that convince you?
Sort of. I think I get the point a little bit.
Do you want to ask a follow-up?
But still, it's the runtime to change 4x. If doubling causing the runtime change 4x.
It's true that 4x and x look different when we draw them, but they're different in a way that we don't care about when we talk about computational complexity. Because at the end of the day, we're never going to actually evaluate this function and say, oh, n is 1,000, and so therefore I plug it in, and now f of x is 1,000, because 1,000 what? Like, it's not going to be 1,000 seconds or minutes anyway. So we're never going to really calculate the number anyways. We're just going to use this language to talk about the growth rate.
Yes, so it's like 8x divided by 4x is still 2. It's not 4. Exactly.
That's right. That's right. So if maybe if I call this f and this g, then I think this is similar to what you're saying. But f of 2x is 2 f of x, and g of 2x equals 8x equals 2 g of x. So at the end of the day, both have these properties that doubling the input just doubles the output.
I see. Thanks.
I'm guessing a lot of people had the same question, so I was happy to spend time on it. Yeah, any other questions? Okay. So here's this table of common run times. And these are mainly the only ones we're going to encounter. Of course, you could have any function like sine of n, but that would be ridiculous because why would the running time go up and down again with a period of 2 pi or whatever? These are the ones that you will typically encounter in real life. So O of 1 means it's constant. It means I don't even care what n is. I'm always going to take the same amount of time. And that's like the function. The function 1 is just, you know, a horizontal line. It's just the same no matter what the input is. So the searching in a set, I guess I'm giving away. Never said that. Okay. We'll talk about that in a minute. But this means that it's called constant time, and basically whatever the input is, it's going to take the same amount of time. Whatever the size of the input is. That's what I meant to say. Logarithmic, log n. So what does that mean? It means that if I double n, then the running time is just going to go up by a constant, like say 1. So I'll double n and it'll just get 1 second slower, and I'll double n again, it'll just get 1 second slower, because that's essentially what the log function does. That's amazing, right? Because that's not that different from O of 1. It's extremely slow growth. O of n we just talked about, like searching in a list. That's called linear time. And if I double n, then the running time doubles. And notice I don't have 2n and 4n and all that stuff on the list. We call all of those things linear time because for our purposes they're the same thing. They have this property of double the input, double the output. O of n log n, that's called linearithmic. That's pretty similar to O of n, but just grows a little more, but not in a way that we really care. Generally, log n we don't care much about for our purposes because it's going to be very small. O of n squared means, I think the next activity is just doomed. So let me prioritize learning over sticking to the plan. So let me just relate these things to what we were already talking about, which is that first case was searching in a set. That was O of 1. It was however much stuff was in that set. We doubled the amount of things in the set. It still took the same amount of time. O of n, we had when we were searching inside of a list or when we were multiplying a bunch of things by a number. O of n log n, that was actually our sorting. So I said that it was, when I went with the sorting with the numpy function, that I said if you double the size of the array, it slightly more than doubles. It was actually this. N squared was my not very good sorting code, that if I doubled the size of the input, then it went up 4 times. And you could have cubic, which is n cubed. So if I double the size of the array or the input, it takes 8 times as long. And I could have any other power, n to the 2, n to the 3, n to the 4, n to the 5, whatever. And I could have exponential, O of 2 to the n, which is the most horrendous running time, which says that if I double the size of the input, the runtime actually gets squared, which isn't that helpful of a way to think about it. But the way I would think about this exponential thing is if I just make the array 1 bigger. So I had 1,000 things in my array, and now I just do 1,001. That causes the runtime to double. So you could think of how incredibly bad that's going to be, because every time you just make it 1 bigger, the running time doubles. That's going to get out of hand very, very fast. Okay. So any questions or comments about this? Karan.
So in your code, your loop is running for n times. So how you are taking the n squared inside?
Yes, great question. So let's talk about this, and then we'll take a break right after that. So Karan was asking, sorry about all the scrolling. Here. So this was my very slow sorting code, and Karan was saying correctly that it's typically kind of a pattern that if I'm looping through n things, that's kind of linear O of n runtime. Like when I was multiplying everything by 2, I was looping through the array. And generally, when you see a loop, that means I have to do the thing n times, which is kind of linear behavior. So why is this thing O of n squared or quadratic? The answer is this. Yes, I am doing something n times, but what am I doing inside of the loop? Well, this line of code itself actually takes O of n time, because argmin has to search through the whole array and find me the index of the smallest one. Is this the smallest one? No. Is this the smallest one? Is this the smallest one? Is this the smallest one? It has to look through all of them and keep track of which one was the smallest. And so running that one line of code is itself linear time. If my array was twice as big, that argmin would take twice as long, because it is looking through every single thing. And so now the argmin is linear time. It's O of n time. It takes n steps, so to speak. But then I'm doing that whole thing n times in that outer loop. And so I basically multiply those together, and I get n times n, which is n squared. So now if I double n, then I'm doing, so this line of code is going to take twice as long, and I have to do it twice as many times. So in total, it's going to take 4 times longer. Forgot your name.
Ithar.
Ithar.
Yeah. So the argument, like it takes less steps every time because.
Aha. Okay. Now we really get into it. Okay. Ithar is saying that, well, actually, I was exaggerating. It's not as bad as it looks, because the argmin is actually only looking through a subset of the array, because I'm sorting this array as I go along. So let me. So here I am. I've already sorted part of the array, and now I'm right here. I'm halfway through the algorithm. I've already sorted put the first 4 in order, 1, 2, 5, and 8. And now what I really want to do is say the 2 is the smallest thing of what's left, and then I want to swap the, okay. 9. The 9 is the smallest of what's left, and now I want to swap the 9 and the 99 so that the 9 is in its proper place here after the 8. So what Ithar was saying correctly is this argmin is not having to search through the entire array. It's actually only having to search through half of the array, which is absolutely true. So how many steps is this really taking? Well, the very first time, and just to remind you, this I colon is subsetting the array. So that's what's causing this in terms of code. Because first I is 0, so x 0 colon is taking the whole array, and then I is 1, and x I colon is ignoring the first one, and so on. So how many steps is this really taking? Well, the first time the argmin needs to look through n things. Is this the smallest? Is this the smallest? Is this the smallest? Is this the smallest? And then the second time you go through the loop, it's only having to look through n minus 1 things because of that subsetting. And then the third time, it's only having to look through n minus 2 things. And then this is going to go on and on and on. And at the end, it's only going to have to look through 3 things, and then 2 things, and then 1 thing. So this is actually the number of steps. And this is an arithmetic series. And the actual number of steps here is minus 1 or plus 1.
And plus 1.
Plus? Okay. Well, either plus or minus there, but it's something like that. Which no, it's got to be minus. Okay. Which is something like that. And this goes back to fundamentally what is big O notation. And we had Rock's question before. What about the difference between n and 4n? So we actually don't care about the difference between that, and we just call it O of n. Another thing we don't care about in big O notation is the difference between n squared and this, which is slightly less than n squared. Because at the end of the day, if it's true that if I double n, maybe it's not exactly doubling, but this is the dominant term here. So when n is really, really huge, like if n is 1,000,000, 10 to the 6, this is going to be 10 to the 12. This is peanuts, right? We can just ignore this. And all this running time complexity stuff, the way to kind of think about it is what happens when n is really huge, and then I grow it some more. And when n is really huge, yeah, the difference between 10 to the 12 and 10 to the 12 minus 500,000, we just ignore that. So again, there's like a formal mathematical way of thinking about it, but for our purposes, we just look at the fastest growing part and ignore everything else. So for our purposes, this is actually the same as if this inner piece of code here took n steps every time, even though that's not quite what's happening. Yeah, your name?
Gaurav.
Gaurav.
Yeah, that will be n square by 2 plus n by 2. And we remove the constant.
Yeah, right. Thank you.
And that will be plus.
So that's right. I forgot about this over 2. And the reason we don't care about this over 2 is going back to this difference between n and 4n. So as far as growth is concerned, well, this is too small for us to care about. We only care about this. And furthermore, this n squared over 2, when we double n, it goes up 4 times. So at the end of all this mess, we just say O of n squared. Let's take our break and resume at 10:20. Put this back as a plus. Hopefully we're all good now. So next thing I want to do is, well, I kind of stole my own thunder in the sense that I already drew some of these on the board, but I have some nice pictures for you about what these functions look like. You should disregard this code. I need the code there to generate the plots, but the code is not really part of the course. Just the plots are part of the course. So let's just look at the plot. This plot shows n versus different functions of n, just like we have over here, but I have a whole bunch of functions for you to look at. So I have the function 1, which is just this horizontal line. I have log n, n log n squared, 2 to the n cubed, and so on. So these are useful to just look at and think about, and you can see how some of them are growing really, really fast. And even though n is like 5, the function is already huge. So you can just, the point of this picture is really for you to A, start to think about what runtimes are desirable or undesirable, and it's going to depend on your problem. Right? Because for the problem you're working on, maybe n squared is the best you can get and it's good enough, and maybe a different problem, n squared is too slow and it's not going to work and you need something better. It depends on the details. But at least think about these things, look at them, talk about them with your friends, and at least keep in mind how much faster some of these curves are growing than some of the other ones. Like this really matters. You can have code that is way, 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 way slower or faster depending on what algorithm you're using. So people often like to look at log-log plots. So this is a plot where the x-axis and the y-axis are both logarithmic. That's why you see 10 to the 20, 10 to the 40, 10 to the 60, 10 to the 80, etc. And the main point I'm trying to communicate with this log-log plot is that 2 to the n is just way, way, way more horrible than all of the other things. Like they're all just smushed together looking reasonable compared to 2 to the n, which is just an utter disaster. So in general, exponential growth, you will typically not have a practical, useful algorithm that grows exponentially with the input size. There's some nuances we're not really going to talk about in this class, like there's some randomized algorithms where maybe, or certain algorithms that in the worst case, if you try to prove it, you'll say, oh, in the worst case it could be this, but in reality it's never actually that, and in practice it's kind of fine. We're not going to get into those nuances. Yeah, Tom.
Do we ever create 2 to the n out? Like, do we ever actually create that?
We will make one in this course, but you will not really want to do this in real life.
You don't want to, but is it hard to accidentally do? Or?
Oh, is it hard to accidentally do? Probably not, but it'll be easier to talk about that next week. Yeah, next week we'll see what code looks like that is actually that slow. Right, so I just, in the original plot, just scrolling up here, n cubed was actually ahead of 2 to the n, but that's just because the plot didn't go far enough. But 2 to the n is actually much, much faster growing. Excuse me. Okay, so I'm just going to remove 2 to the n and plot it again. And now, this is kind of cool. On this log-log scale, you can see all of these different things and how you have constant, logarithmic, linear, logarithmic, squared, cubed. And actually, when you plot things on a log-log scale, you can actually look at the slope of the lines. And this n cubed should have a slope of 3, and this n squared should have a slope of 2. I didn't scale the axes right. Anyways, point being, you can really see clear differences between them, but they don't look that drastic on the log-log plot, but they could actually be quite drastic. Okay, so that's that. The next thing I wanted to say, I guess we've already talked about, which is constant factors are not important. So that was Rock's question. If an algorithm takes 2n steps, we write big O of n, not big O of 2n, because those both grow in the same way, and so for our purposes, it's just not worth making that distinction. Another thing is, big O does not equal speed. So sure, log n grows much slower than O of n. If I have code that takes log of n time, does that mean it's going to be faster than code that takes linear time? Not necessarily. So all this big O stuff is useful to a point, but it cannot always be trusted to say this algorithm has better big O, therefore it's faster. Because again, we've thrown away that constant factor. And if the actual time in seconds is 1,000,000 times log n, and the other one is 0.00001 times n, and n is 100, then the log n one is actually going to be way slower. So they are useful. It is important to know this kind of language and be able to talk about these things, but you can't just look at it and immediately say this code is going to take more seconds or minutes to run than that code. It's just going to tell you something about growth. And even as far as the growth is concerned, it's especially valid when n is already big. But as we saw here, there's some other details that we're sweeping under the rug. So take these things with a grain of salt is basically what I'm saying. And we're going to see an example of this in lab 2, where for certain small input sizes, small n, I don't even remember. I think the linear time thing is going to run faster than the logarithmic time thing. But then when n gets big enough, the logarithmic one will eventually become better. So what affects the big O? Well, basically the algorithm. So the sorting things, we haven't talked about how the fancier sorting works, but they're different algorithms. They perform different steps, and at the end of the day, one actually does more work than the other one. So that's a different algorithm. And different algorithms are going to give you different big O's. But what affects the constant? And by the constant, what people mean is this 2 or whatever it is, the constant that is actually multiplying n or n squared or whatever that we've just thrown away. So here it's like we have this constant of 1/2 that we're just ignoring. Excuse me. So what affects the constant factor? Well, it could be the algorithm, but it could also be the implementation. So some algorithms might take 2n steps, some might take 100,000 n steps. Each step might take a minute in one case or a second in another case. But furthermore, there's all these details like, C is often going to be faster than Python, or I'm using NumPy, which is going to be better than using base Python, or I have a better laptop than this other person, or a worse laptop, or other stuff like that. So there is a lot of things, or am I running a bunch of other things on my laptop while I'm running Python? That could make it slow too, right? So it is very, very hard to know how long something is going to take in seconds or milliseconds, like accurately. There's just too many factors going on. And so we don't really need to quantify all those things precisely, but we should kind of have them on our radar as things that could influence how long code is going to take. And we'll talk more about those in the last lecture of the course, lecture 8. OK, moving on. Space complexity. So space complexity is about this issue of memory. So my computer has, you can do this on your computer too, or you can do, about this Mac or whatever. You can see how much memory I have here. I have 8 gigs of RAM on this laptop. That's different than my hard drive. It's not really a hard drive anymore, but it's the amount of memory that I have on my laptop to put stuff in. So I have about 8 gigs of RAM or memory. And a single number typically takes around 8 bytes to store. So a number like 2.7 or whatever, a number typically takes 8 bytes to store in memory. So if I have 8 gigabytes of RAM and a number takes 8 bytes, that means I can store around 1 billion numbers. So anything I need to do that requires me storing more than 1 billion numbers at a given time, it's just not going to work. My computer is going to just throw up its hands and say, hey, I can't do what you're asking me to do because I cannot fit this amount of stuff in memory. And so in addition to time complexity, we typically also care about space complexity, which is how much space at a given time do you need to execute this code properly. And we can use big O for that in the same way as well. We can say if I double n, do my space requirements double? Do they stay the same? Do they go up 4 times, etc.? Also, even though I have 8 gigabytes of RAM on my laptop, that doesn't mean I can use all of them necessarily for what I'm doing, because I have other stuff going on, like the operating system, not just Python. OK. So with time complexity, we tend to think more about the algorithms. With space complexity, we tend to think more about the data structure. So here's an example. If I'm just making a NumPy array with n spots in it, so I have n zeros, then the space complexity of that is going to be O of n, because if I make a NumPy array that's twice as big, well, it's twice as big, I guess. I don't really know a better way of saying it, but if it's going to require double the space if I make the array twice as big, and so that's going to be O of n. So how about this? Does anyone want to take a guess at the space complexity of this 2-dimensional array, an n by n array? N squared, right. So we talked about 2-dimensional arrays briefly in programming, but it's essentially a table or a matrix or whatever you want to call it. Has n rows and n columns, so the number of spots in there is n squared. And so, in fact, the amount of numbers in there is literally n squared, and the space complexity of O of n squared, if I double n, I'm going to need 4 times the amount of memory to store that array. So how about this one? A 3-dimensional array with n rows, n columns, and 5 slices, or whatever you want to call it. Yes, this is also n squared. Because the 5 is just 5. It doesn't depend on n. So this is basically 5 2-dimensional arrays stacked on top of each other, or maybe 1, 2, 3, 4, 5. And so the number of elements in here is n times 5, or 5n squared. And 5n squared, for the purposes of big O, is the same thing as n squared. So how about this one? 3-dimensional array, an n by n by n NumPy array. Anyone?
n cubed.
N cubed, yes. So how many spots are there in this array? Well, it's an n by n by n array. It's in fact kind of a cube-like data structure. And so if I double n, so for example, if n is 10, there's going to be 1,000 elements in here. 10 by 10 by 10, and now if n is 20, there's going to be 8,000 elements in here. The size has gone up 8 times if I double n, so that's n cubed. Did we? I don't know if we even made any 3-dimensional arrays in the programming course. Did we? I don't think so, but I can just do it. well, let's do random. Ah! So I would just access it like this, for example. Okay, how about this one? X equals np.0 is 5. What's the space complexity? Constant, yes. O of 1. So there's no n here. It doesn't even appear on the page. So whatever n is, this thing is just going to have 5 numbers in it every time. So that's O of 1. And let's skip these other ones in the interest of time. You can look at